Now that we've defined the derivative as a limit of again, another special difference quotient, I want to spend some time doing a couple more examples to illustrate the process for different types of functions, and then just say a little bit more about what this derivative can represent. Right? So let's just start with some examples. And what I will do, since we've already done several examples as far as finding the slope of the tangent line at a specific point and then finding the equation of the tangent line, I'll focus on computing the derivative in these videos. Right? So let's start with this type of function. Let's say it is x cubed minus 4x plus 5, right? And the idea is to find f prime of x. And as a reminder, f prime of x is what we use to indicate the derivative. So it's something that is going to be derived from this function, and the way we derive it now is through a limit, right? So let me write it down again symbolically. So f prime of x, which is the one notation for the derivative, it is the limit as h approaches 0 of this difference quotient, right? Provided the limit exists. So let's go through and do this. Now, for this type of function, where we have a slightly larger power of x, the algebra might be a little bit more tedious, but let's see what it looks like. So let's first compute the f of x plus h, and maybe it would be helpful to kind of do that off to the side, right? So let's do f of x plus h. Well, what does this tell us to do? It says go to the function f, and wherever there is an x, replace it with the quantity x plus h. So we will have x plus h cubed minus 4 times the quantity x plus h, and then plus 5, right? So the thing that makes this a little bit more tedious is expanding this binomial, because now the exponent is a 3. So let me maybe go up here. So just looking at this, x plus h cubed, that by definition is x plus h times x plus h times x plus h. How would we do something like this? Well, there are different ways. We can do that product first that I've put in the square brackets, and if we do that first, we end up with, so when we FOIL, and again this is going to be this part of it in the square brackets is a perfect square, so we will end up getting x squared plus 2xh plus h squared. And then I have to go through and distribute the x to each of these 3 terms, and then this h to these 3 terms as well. So let's start with the x times x squared, that's x cubed, x times 2xh, that is 2x squared h, and then x times h squared is simply x times h squared. And now let's distribute the h, so we will have h times x squared, like that, and then h times 2xh gives us 2xh squared, and then finally h times h squared gives us h cubed. Now let's see if there are any like terms. Well, there's only one x cubed, so that comes down. But if you look at it, we have 2x squared h, and then here's another x squared h. You might say, well, it's not written as x squared h, but because it's a product, we have that commutativity property where we know that x squared times h is the same as h times x squared. And I have 2 of them here, and I have one more here for a total of 3. So I'll write this as 3x squared h. And also take a look at this. We have 1xh squared and then another 2xh squared for a total of 3xh squared. And then all we're left with now is the plus h cubed. So wow, that's quite the endeavor. But again, we have all the algebra that we need to handle these types of expansions. We just use our distributive property over and over and over again. All right. So what does this mean? It means that this replaces the x plus h cubed, right? So I'll have x cubed plus 3x squared h plus 3xh squared plus h cubed. And then when I distribute the -4, I'll get a minus 4x minus 4h, and then finally a plus 5, right? So this alone is what we get when we expand and simplify and collect all the like terms that we can possibly collect when we do the f of x plus h. All right, so I'm going to give ourselves a little bit more room. So we have the limit as h approaches 0. So we're going to start by writing this down, and I'll put it in square brackets so you can see each of the expressions that are being used. So this is a long one. We have x cubed plus 3x squared h plus 3xh squared plus h cubed minus 4x minus 4h plus 5, right? So again, that's the f of x plus h term. Now we get to subtract the original function. So we have x cubed minus 4x plus 5. All right, so now that's the top, and now this is all over h. Right? Almost feel like we should take a little breather, do some yoga. But let's keep going. All right, so what do we have? Now let's look to see what terms will cancel out. So we have an x cubed here, and then minus x cubed right here, right? And again, that minus is a part of our difference quotient. Let's see what else. We have a negative 4x, and over here we're subtracting negative 4x. So again, those will cancel out. And then we have a plus 5 and then a minus plus 5, right? So there we go. So all the things that are circled, those terms are eliminated, and that really does simplify what we have left. There's still a few terms to deal with, but it's certainly becoming a more reduced problem. So what do we have left? We have a 3x squared h plus 3xh squared plus h cubed minus 4h, and that's all over h. Now, something that always happens when you do this type of process, this derived process via the limit, and you start with a polynomial, when you expand and simplify the numerator, all the terms that don't have an h will cancel out, right? I mean, it is a given, right? So if you get to this part, after you thought you simplified the f of x plus h minus f of x, if you're still having terms that have just an x in them, right? Then it means something went awry with your algebra, right? So far things are looking good because every term that's left over has an h. Well, why is that good? Because I can factor an h out of the numerator. So the limit as h approaches 0, we can take out an h and look at what we have left. 3x squared, and then plus 3xh, and then plus h squared, and then minus 4. And then this is all over h. So now we can reduce our difference quotient even further. And what goes? That factor of h, that factor of h. And it's just slowly, we're getting to a point where now we can actually evaluate the limit. So we're left with the limit as h approaches 0 of the expression 3x squared plus 3xh plus h squared minus 4. And now, since I've gotten rid of the h in the denominator, my limit for sure isn't going to be, it's not going to be indeterminate, because I can evaluate this at h equals 0, and the middle terms, the two middle terms, will cancel out. So what are we left with? We're left with 3x squared minus 4. And this is the derivative of our original function. So in fact, let's just kind of state that as a summary of everything that we've done. So if we start with this polynomial, then when we derive this derivative, we end up with another polynomial, right? There we go. All right, so that's the derivative. Now, as I said, I'm not going to worry about using the derivative to find the slope of the tangent line in this particular video. I want to focus on this process right here, right? So let's do another example of that process. And let's do a different type of function. Let's take okay, so let's do this. So let's take f of x to be equal to, let's say, the square root of 2x plus 1. All right, so a root function, right? And again, the root functions are sometimes trickier, but we've seen how to handle square roots in limits that are indeterminate. We probably are going to end up having to do some kind of rationalizing in this process. All right, so let's write down our derivative. It is the limit as h approaches 0, f of x plus h minus f of x over h, right? So now let's see. Now the thing with this one, it's not going to take as long to set this up because I don't have a lot of foiling or expanding to do, right? So let's see. So here, again, the first term in the numerator is telling me take my function f, and wherever there's an x, replace it with x plus h. So I'll have the square root of 2 times the quantity x plus h, and then plus 1, right? And then I have to subtract the original function, square root of 2x plus 1, and then this is all over h. So it doesn't look quite as, overwhelming as the previous one when we had this big expansion, or relatively big. I mean, let's be honest, it wasn't that big, but it was certainly bigger than the expansions that we've done in previous problems. But we still have something that's indeterminate, because if we try to plug 0 in for h, well, we're going to end up with the square root of 2x plus 1 minus the square root of 2x plus 1, so we'll have a 0 in the numerator, and for sure we'll have a 0 in the denominator, right? So what we need to do is rationalize this. So what I'm going to do is, I'm not going to do it off to the side, otherwise I'll probably run out of room. But let's do the rationalizing here in the middle, but I'll use a different color just to say here is some side work that we're going to work on. So if I take what is there to begin with, And under the first square root, distribute the 2, I will have 2x plus 2h plus 1. And then I have minus 2x plus 1. And then all over h. So to rationalize, what we have to do is multiply the top and bottom by the conjugate of the top, which is the two terms stay the same, but I change that minus to a plus. So it's going to be times the square root of 2x plus 2h plus 1 plus the square root of 2x plus 1 all over the same thing. Square root of 2x plus 2h plus 1 plus the square root of 2x plus 1. And what we have in the numerator is the difference of two squares. This is like my a minus b, this is like my a plus b, and we know how that, when we expand it, what happens. The middle terms cancel out, and we're left with a squared minus b squared. Right? So if this is my a, well, when I square it, the square root is going to go away. And same thing here. If this is my b, when I square it, it's going to go away. So the top, so think of the top as like this. This is what we're doing. Right? So let's see here. So this is equal to, so when I apply my difference of two squares formula, I'll have this term, which is 2x plus 2h plus 1, so that's my a squared, minus b squared, which is 2x plus 1. And then in the bottom, again, I have h times this long expression. Root 2x plus 2h plus 1 plus root 2x plus 1. All right. Now look at what happens in the numerator. Something similar happens in this numerator as well as similar to what happened in the numerator in our previous problem with the polynomial. Look, we have a 2x minus 2x. And then we have a plus 1 minus plus 1. So look at what we're left with in the numerator. It's just a 2h. So it doesn't really seem that daunting anymore. So we have 2h over h times the quantity, root 2x plus 2h plus 1 plus root 2x plus 1. And then now we have a common factor because the h is a factor in the numerator, the h is a factor in the denominator. So that goes away, right? So that's what this difference quotient, when we rationalize and reduce, this is what it reduces to, right? So now I'm going to switch back to white because now I know I can see how this is all going to play out, right? So this is the limit. Let me go up some more as h approaches 0. And now I put this here. So I have 2 over root 2x plus 2h plus 1 plus root 2x plus 1. And now I can see for sure it is not going to be indeterminate because I don't have a 0 in the numerator, and I'm not going to get a 0 in the denominator either, because if I evaluate this as h approaches 0, this term approaches 0, so that term goes away, and I'm left with 2 over root 2x plus 1 plus itself root 2x plus 1. So what I end up with is I end up with 2 root 2x plus 1 in the denominator. because I have something plus itself. So it's doubled. So I have 2 root 2x plus 1. And look even further. I have now a 2 in the numerator and a 2 in the denominator. So what do we have? We have 1 over the square root of 2x plus 1, right? And that's the derivative of our function. All right, so let me again kind of summarize what we just did. So if, and we might even have forgotten what our original function is, it's the square root of 2x plus 1. So if that's the function that we start with, and then we do this derivation, so its derivative is equal to 1 over root 2x plus 1. Kind of interesting, because we look at this particular process and the derivative just ends up being the reciprocal of the original. Maybe there are some patterns there that we'll be able to see later on, right? Okay, so there are a few examples of how the derivative process, the derivation process, I should say, how it works for different types of functions, right? So to wrap this up, I want to mention a couple things about the derivative. One is something that we've mentioned prior, and then one is something that's new. So what I want to, so let me just take us back to where this all started. Remember, it started with a simple secant line. A simple secant line. And we found the slope of that secant. And it was equal to that, just the difference quotient now, the f of b minus f of a over b minus a. And, that would be our a. That would be our b. And then this is f of a, and this is f of b. All right, so that's where it started. That's where this whole thing started. And in addition to calling it the slope of the secant line, you might recall that this is also defined as what we call the average rate of change, right, of f of x over the interval x greater than or equal to a, x less than or equal to b, right? So now we have a way of computing the slope of the tangent line at any point, provided it via this limit, provided the limit excuse me, exists. So again, let's say we have this, and now I just need a single point, call it A, and then the tangent line is kind of there, right? And there's no second point, but we know how to find the slope now. So we're saying that the slope of the tangent line. So this would be, using all the notation that we've introduced, this would now be f prime of A, right? That's what it would be. And then again, let me just remind you what f prime of x is. So we would first do this derivation process, right? Use the limit of our difference quotient. And after finding f prime, we can then plug our x value in, and that will give us the slope of our tangent line. So, we have this kind of as an analogy, right? Graphically or geometrically. This is kind of the analogy here, right? And with the limit of the difference quotient, whereas this is just the difference quotient. There's no limit there. But what is the analogy in terms of this verbal description? In other words, what do we call this? Is it just the slope of the tangent line? Well, it seems like this difference quotient can be interpreted two ways. Geometrically as the slope of a secant line, and then almost physically like the average rate of change of a function. Like how on average, at what rate does the function change over this interval? Well, it turns out there is a rate interpretation of the derivative as well. And this is defined as, and we call it, right, the instantaneous rate of change of f of x at x equals a, right? So the word average now becomes instantaneous. So this is the instantaneous. It's still a rate because it's a slope, right? And that's what a slope is. It's a rate of change. But this one is not an average because it's not over an interval. It's at a specific point. So it's the instantaneous rate of change of our function, right? But look at how the wording changes. At x equals a, right? So at an instant, at what rate is my function changing, right? So again, let's see. So we have now the complete kind of analogy or parallel between these two things. But here are the key differences. Average versus instantaneous. Over an interval versus at a point. That's the distinction between just an algebraic calculation versus a calculus calculation, right? So I think this is a good thing to end with. After all, the process end with something a little bit more conceptual, but this difference is key. This difference is key. And the fact now, if we want to compute instantaneous rates, we have to look no further than our derivative, right? And certainly that's something we're going to be doing a lot in the future. See you in the next video.